In the previous lesson, we learned that the entropy of mixing for two ideal gases could be written very simply in the following way. The change in the entropy for mixing, and I'll make this, I think we reported it as a molar entropy, was simply given by minus R times the sum over all the components of the mixture times the mole fraction of each component times the log of the mole fraction. So this made for a very tidy formula and a very simple expression. And the question is, how much does that carry over to a solution? So what I want to consider is the definition and the properties of ideal solutions. Now, an ideal solution in this case is not going to be like an ideal gas, in that an ideal gas, there are no interactions between the particles. They just bounce off one another elastically. They don't have any intermolecular forces that go on. In an ideal solution, we can't really do that because it wouldn't stay a solution. It would just dissipate as a gas. So what we can do, though, is say that the intermolecular forces between the particles in a mixture of molecules or atoms, the intermolecular forces are all the same. So in other words, a substance that might be in a mixture can't tell that it's in a mixture because all of the other particles to it look the same as itself. So what this means then is that there's a balance, if you will, and the properties of the liquid don't change when you throw two liquids together and make a mixture when it happens to make an ideal solution. Well, let's see what this might mean in terms of a thermodynamic consequence. Ordinarily, we might write the free energy, the Gibbs energy for mixing as follows. We might write it as a difference between the Gibbs energy of the solution, and so I'll write that as generically as a function of temperature, pressure, and the numbers of moles of each of the substances that make up that mixture. Let's just say it's a two-component mixture. So that would be the end result. So then we would subtract the two things that we're mixing together. So if I have component 1, I'm going to use the star to indicate a pure substance. It will have temperature, pressure, and the number of moles of substance 1. And also we would be subtracting the pure Gibbs energy for substance 2, which would have these as its functional variables. All right, so when we're putting this together, we can identify some of these things as follows. For example, I could identify this Gibbs energy of the solution as simply being the number of moles of the chemical potential of the solution for component 1 plus the number of moles times the chemical potential for the solution for particle 2. Now, I haven't really defined those things elaborately, but I hope you'll play along with me and accept those as real entities. Then we would have minus N1 times the chemical potential of substance 1. Now, this will be as a pure liquid. So I'll denote it as liquid sub 1, and I'll put the star up here to indicate that it is a pure liquid. And the same sort of expression for number 2. So again, this is a liquid for component 2, and it's a pure substance. So this would formally be the way we might write down this change in the Gibbs energy. But how can we relate that to other quantities that we know? Well, I want to go back to this expression that we had before for the change in the molar entropy. Now, if it weren't molar entropy, I might rewrite this as follows. I might rewrite this as minus N1. I'll assume a two-component mixture. N1 times R, so minus N1 times R times the log, times the, mole fraction of 1, log of mole fraction of 1, minus N2 of R, mole fraction of 2, log of mole fraction of 2. All right, I hope you'll forgive my blunder there on the mathematics. All right, so this is a fairly simple expression, but now I've made the entropy be for some variable number of moles. Okay, so now how would I convert this somehow into a Gibbs energy? Well, I know that if I took the partial derivative of the Gibbs energy with respect to temperature at constant pressure, and we'll say at constant moles, that I would get minus S. So I can basically carry this over to indicate that the partial derivative of the Gibbs energy for mixing with respect to temperature at constant pressure and moles would simply be minus the delta S of mixing for this process. So now I can plug this expression down in here, and when I integrate over temperature, the only parts in here that are dependent upon temperature, well, there is no parts that are dependent on temperature. It's a totally temperature independent expression. So that would tell me then that my my Gibbs energy for mixing would be equal to minus T times what I found for the entropy of mixing. And so that would give me, the minus signs will cancel. I'll have N1 RT x1 log x1 minus, plus N2 RT x2 log x2. So again, we see that we can develop, if you will, a fairly simple expression for this Gibbs energy out of this. Now, I could include an integration constant because I had to integrate to get to this, and that integration constant might well include, for example, the enthalpy. But here's where I want to make an argument that will hopefully persuade you that this is a good expression for that Gibbs energy of mixing. If the particles that make up this mixture all have the same intermolecular forces that they had when they were pure substances, the only result of mixing is to substitute nearest neighbors in that mixture. And so what we're doing is we're breaking some of those intermolecular attractions, but we're replacing them with others that have the same strength. The net result of that is that we should have, for an ideal mixture, we should have a situation where the enthalpy of mixing, so I'll write it this way, is equal to 0. And this is something that we would say is always a property of an ideal solution. Now I'll add one more, and that is that when we mix things together, we're going to expect that since those intermolecular forces are identical between the two, we should have no volume change when this happens. So in other words, the delta V is going to be 0 for this process as well. And this is something that we would also relate to the delta mixing of Gibbs energy with respect to pressure at constant temperature and moles. All right, so this is something that we'll say is equal to 0. So in other words, that Gibbs energy of mixing doesn't have any dependence upon the pressure, which is indeed consistent with what we've seen up here in this expression. So the net result for this is that for ideal solutions, we have a free energy, a Gibbs energy and an entropy of mixing that are consistent with one another. The Gibbs energy of mixing is simply the temperature minus the temperature times the entropy of mixing. And we have that the enthalpy of mixing and the volume change for mixing are both 0 in this case. Now we'll explore some other consequences of ideal solutions in the upcoming videos.